Tonight, we begin with a question that has quietly shaped every moment of your existence. Why does the sun rise each morning? Why does water always flow downhill? Why can we predict when the moon will be full, when the seasons will change, when a dropped stone will hit the ground? The answer lies in something both profound and comforting. Reality follows patterns. It operates according to rules that we can discover, understand, and rely upon. This isn't mere human wishful thinking or an illusion of order imposed upon chaos. It's something far more beautiful and reassuring. The universe itself is predictable. Now, settle back and let your mind drift gently into this exploration. We're going to journey together through the quiet mathematics that govern everything around us, from the smallest quantum interactions to the vast sweep of galactic motion. And as we do, you might find that understanding why reality is predictable brings a deep sense of peace, a recognition that beneath all the complexity and uncertainty of daily life lies a foundation of reliable, discoverable truth. The story of predictability begins with something deceptively simple: patterns. Look around you right now, even in the dim light of evening. The regularity of your breathing, the steady rhythm of your heartbeat, the way shadows fall consistently across familiar objects. These aren't accidents. They're expressions of deeper mathematical principles that have been operating since the beginning of time. Consider the spiral of a seashell resting on a distant beach. That spiral follows a precise mathematical sequence discovered centuries ago by an Italian mathematician studying rabbit populations. The Fibonacci sequence, where each number is the sum of the two preceding ones, appears not just in population growth, but in the arrangement of sunflower seeds, the pattern of pinecone scales, and the graceful curve of galaxy arms spinning slowly through space. This same sequence governs the branching of rivers, the structure of tree limbs reaching towards sunlight, and even the formation of weather systems swirling across continents. What makes this remarkable isn't just that these patterns exist, but that they emerge from simple rules repeated over and over again. A sunflower doesn't consciously arrange its seeds according to mathematical principles. Yet the most efficient packing of seeds in a circular space naturally produces the Fibonacci spiral. The mathematics isn't imposed from outside. It emerges from the fundamental constraints of space, efficiency, and growth. This points to something profound about the nature of reality. The patterns we observe aren't arbitrary. They reflect optimization principles that operate throughout the natural world. Systems naturally evolve toward configurations that maximize efficiency, minimize energy, or optimize information storage. These principles are so fundamental that they appear at every scale, from the quantum realm to the cosmic. But patterns alone don't explain predictability. For that, we need to understand something deeper: physical laws. These aren't rules imposed by some cosmic authority. They're descriptions of how energy and matter consistently behave under similar conditions. When we say that objects fall toward Earth at an acceleration of approximately 32 feet per second squared, we're not describing a command that objects must obey. We're describing a relationship between mass, distance, and the curvature of space-time that produces the same result every single time. This consistency is what makes prediction possible. If physical laws changed randomly or operated differently in different places, we couldn't anticipate future events based on present conditions. But they don't change. The same gravitational principles that govern the fall of an apple also govern the orbit of planets, the formation of galaxies, and the dance of binary stars millions of light years away. The mathematical language that describes these laws is itself revealing. Einstein once remarked that the most incomprehensible thing about the universe is that it's comprehensible. Why should reality be describable through mathematical equations? Why should the same mathematical structures that exist in human minds also appear to govern the behavior of quarks, quantum fields, and cosmic expansion? Recent research suggests an answer that's both elegant and surprising. The equations of physics themselves follow statistical patterns. Just as human languages follow predictable distributions where common words appear much more frequently than rare ones, the mathematical operators in physical equations follow similar statistical laws. This suggests that there might be meta-laws, mathematical principles that govern not just physical phenomena, but the very structure of the laws that describe those phenomena. Think about what this means. We're discovering that the universe operates not just according to mathematical principles, but according to mathematical principles that themselves follow deeper mathematical patterns. It's mathematics all the way down, creating layer upon layer of predictable structure. This mathematical foundation extends into the realm of human behavior in ways that might surprise you. Analysis of millions of cell phone users has revealed that human movement patterns are 93% predictable. Despite our sense of making free choices about where to go and when, our aggregate movements follow statistical laws as reliable as those governing gas molecules or planetary orbits. This doesn't mean human behavior is rigidly determined. It means that even complex decision-making processes, when viewed at the appropriate scale, exhibit predictable statistical properties. Individual choices may seem random, but collective behavior follows discoverable patterns. The same principle applies throughout nature. Individual gas molecules move chaotically, but the pressure and temperature of the gas as a whole behave predictably according to thermodynamic laws. This reveals one of the most important distinctions in understanding predictability. There's a difference between deterministic predictability, where we can specify exactly what will happen, and statistical predictability, where we can specify the probabilities of different outcomes. Both types of predictability are real, reliable, and scientifically valuable. Weather provides a perfect example of this distinction. Individual weather systems are chaotic, meaning that tiny differences in initial conditions can produce dramatically different outcomes over time. This is the famous butterfly effect, where a butterfly flapping its wings in Brazil might theoretically trigger a tornado in Texas weeks later. Because we can never measure initial atmospheric conditions with perfect precision, long-term weather prediction remains impossible despite our sophisticated mathematical models and powerful computers. Yet weather isn't truly random. It follows the laws of fluid dynamics, thermodynamics, and electromagnetic physics with perfect consistency. Short-term weather forecasts are remarkably accurate. Seasonal climate patterns are highly predictable. And even chaotic weather systems exhibit statistical regularities that allow us to predict average temperatures, rainfall patterns, and storm frequencies over longer time periods. This illustrates a crucial principle. Chaos doesn't eliminate predictability, it transforms it. Instead of being able to predict specific trajectories, we can predict the statistical properties of the system's behavior. Chaotic systems often exhibit what mathematicians call strange attractors, geometric structures in mathematical space that constrain the system's behavior even when specific outcomes remain unpredictable. Consider the coastline of any continent. Its detailed structure is fractal, meaning it exhibits similar complexity at every scale of measurement. The more precisely you measure it, the longer it becomes, as smaller and smaller inlets and promontories are included in the measurement. Yet this seemingly random complexity follows precise mathematical laws. The fractal dimension of coastlines falls within predictable ranges. The statistical properties of their structure can be mathematically characterized and compared across different geographical regions. Fractals reveal how simple mathematical rules, applied recursively, can generate infinite complexity. The Mandelbrot set, perhaps the most famous fractal, emerges from an equation so simple it can be written in a single line. Yet, it produces patterns of breathtaking intricacy that contain infinite detail at every level of magnification. As mathematician Benoit Mandelbrot observed, bottomless wonders spring from simple rules repeated without end. This principle of emergent complexity from simple rules appears throughout nature. The branching patterns of trees, river networks, blood vessels, and lightning bolts all exhibit fractal geometry. The formation of clouds, the structure of turbulence, and the distribution of galaxies throughout the universe follow similar mathematical principles. What appears chaotic and unpredictable at one scale reveals elegant mathematical order at another. Even more remarkably, these patterns aren't just descriptive, they're predictive. Once we understand the mathematical rules governing fractal growth, we can model and predict how these structures will develop under different conditions. We can simulate the branching of river systems, predict the efficiency of circulatory networks, and model the formation of cosmic structures across billions of years. This brings us to one of the most profound realizations about predictability. It operates at multiple scales simultaneously. Quantum mechanics governs the microscopic realm with probabilistic laws that are mathematically precise, even though individual quantum events remain fundamentally uncertain. Statistical mechanics bridges the gap between quantum uncertainty and classical determinism, showing how predictable macroscopic behavior emerges from the statistical properties of countless microscopic interactions. Thermodynamics provides perhaps the clearest example of this multi-scale predictability. Individual molecules in a gas move in ways that are practically impossible to track or predict, yet the collective behavior of trillions of molecules follows precise mathematical laws. Temperature, pressure, and entropy evolve according to equations that have never been observed to fail under normal conditions. The second law of thermodynamics, which describes the inevitable increase of entropy in isolated systems, represents one of the most reliable predictive principles in all of science. It governs everything from the efficiency of engines to the arrow of time itself. Stars burn out, hot coffee cools down, and organized systems tend toward disorder, not because of some cosmic preference for chaos, but because there are vastly more disordered states than ordered ones available to any system. This statistical foundation of thermodynamic predictability points to something even deeper. Information theory, developed in the mid-20th century to understand communication and computation, has revealed connections between entropy, information, and physical reality that suggest the universe itself might be fundamentally computational in nature. If reality operates as a vast information processing system, then its predictable patterns might reflect the algorithmic nature of computation itself. The success of computer simulations in modeling everything from weather systems to galaxy formation suggests that natural processes follow computational principles that can be mathematically captured and predicted. This computational perspective helps explain why mathematical models work so well in describing natural phenomena. If the universe operates according to computational algorithms, then mathematical equations represent our attempts to reverse engineer these algorithms from observed behavior. The fact that we can often succeed in this reverse engineering demonstrates that reality follows discoverable computational rules. Even quantum mechanics, often cited as evidence for fundamental unpredictability in nature, reveals itself to be computationally structured when examined carefully. The Schrödinger equation, which governs quantum evolution, is perfectly deterministic. What appears unpredictable is not the evolution of quantum states themselves, but the outcomes of measurements performed on those states. This distinction is crucial for understanding the relationship between quantum mechanics and predictability. Quantum systems evolve according to precise mathematical laws. The wave function that describes a quantum system at one time completely determines the wave function at any later time, assuming no measurements intervene. The unpredictability enters only when we try to extract classical information from quantum systems through measurement. Moreover, even quantum unpredictability follows statistical laws that are themselves predictable. Quantum mechanics provides precise mathematical rules for calculating the probabilities of different measurement outcomes. These probability distributions have been verified experimentally to extraordinary precision across countless different types of quantum systems. This quantum predictability extends far beyond the laboratory. The same statistical laws that govern radioactive decay also govern the behavior of electrons in computer processors, the emission of light from distant stars, and the chemical reactions that power biological cells. Quantum mechanics provides the foundation for understanding how atoms bond together to form molecules, how those molecules interact to create complex materials, and how those materials exhibit the properties we observe in everyday life. The predictable nature of quantum statistics has enabled technologies that surround us daily. Lasers operate through the predictable stimulated emission of photons. Computer chips function because electrons flow through semiconductor materials according to quantum mechanical laws that are precisely understood and carefully engineered. Medical imaging techniques like magnetic resonance rely on the predictable quantum behavior of atomic nuclei in magnetic fields. This technological success demonstrates that quantum uncertainty doesn't undermine predictability. Instead, it reveals a deeper level of predictability based on probability rather than certainty. The individual radioactive atom cannot be predicted, but the half-life of a large sample follows mathematical laws as reliable as any in classical physics. The specific path of an electron cannot be determined, but the probability distributions that govern electronic behavior are known with extraordinary precision. This probabilistic foundation of quantum mechanics connects to broader patterns of predictability throughout nature. Evolution, for instance, operates through mechanisms that are individually uncertain but collectively predictable. Individual genetic mutations occur randomly, but the overall process of natural selection follows statistical principles that can be mathematically modeled and understood. Population genetics provides elegant examples of this statistical predictability in biological systems. The frequency of different genetic variants in a population changes over time according to mathematical equations that account for selection pressure, mutation rates, and random genetic drift. While we cannot predict exactly which individuals will survive and reproduce, we can predict with remarkable accuracy how gene frequencies will shift across generations. The same principles apply to ecological systems. Predator-prey relationships follow mathematical cycles that can be modeled using differential equations. The growth of bacterial populations follows exponential curves until resource limitations impose logistic constraints. Food webs exhibit network properties that can be analyzed using graph theory and statistical mechanics. These biological patterns reveal something profound about the relationship between predictability and complexity. Complex systems need not be unpredictable. Indeed, complexity often emerges from the interaction of simple, predictable rules operating at lower levels of organization. Individual ants follow simple behavioral algorithms, yet ant colonies exhibit sophisticated collective behaviors that can be mathematically modeled and predicted. The study of such emergent phenomena has given rise to the field of complexity science, which examines how predictable large-scale patterns arise from the interactions of many smaller components. Traffic flow, market dynamics, the spread of epidemics, and the formation of opinions in social networks all exhibit mathematical regularities that can be captured through computational models. Neural networks in the brain provide perhaps the most remarkable example of emergent predictability. Individual neurons fire in patterns that appear chaotic when examined in isolation. Yet the collective activity of neural networks gives rise to predictable patterns of learning, memory formation, and information processing. The brain itself operates as a prediction machine, continuously generating models of future sensory input based on past experience. This neural prediction occurs at multiple timescales simultaneously. Reflexes operate on millisecond timescales, anticipating immediate threats and opportunities. Learning mechanisms operate on scales of minutes to hours, adjusting behavioral responses based on recent experience. Memory consolidation operates over days and years, integrating new information with existing knowledge structures. The predictive nature of neural computation extends to consciousness itself. Our subjective experience of a stable, continuous world emerges from the brain's predictive models of sensory input. When these predictions are accurate, we experience the world as coherent and meaningful. When predictions fail, we experience surprise, confusion, or the need to update our understanding. This predictive processing framework helps explain many aspects of perception and cognition that might otherwise seem mysterious. Optical illusions occur when the brain's predictive models generate expectations that don't match sensory input. Dreams may represent the brain's attempt to maintain predictive models during sleep when sensory input is minimal. Mental disorders sometimes involve disruptions in predictive processing that lead to distorted perceptions of reality. The evolution of predictive capabilities in biological systems reflects the fundamental importance of anticipating future events for survival. Organisms that can predict the location of food, the approach of predators, or changes in environmental conditions have significant advantages over those that respond purely reactively. This evolutionary pressure has shaped nervous systems to become increasingly sophisticated prediction machines. Plant behavior, despite the absence of nervous systems, also exhibits predictive elements. Circadian rhythms allow plants to anticipate daily cycles of light and darkness, optimizing photosynthesis and other metabolic processes. Seasonal changes trigger predictive responses like leaf loss or seed production that prepare plants for changing conditions before those conditions actually arrive. Even at the cellular level, predictive mechanisms operate to maintain biological function. Cells anticipate changes in nutrient availability, temperature, and chemical conditions through sophisticated regulatory networks that can be mathematically modeled. Gene expression patterns change in anticipation of cellular needs, demonstrating that predictive principles operate at the most fundamental levels of biological organization. These biological prediction systems reveal an important aspect of predictability in nature. Prediction isn't just something that scientists do when studying natural systems. It's something that natural systems do themselves as a fundamental aspect of their organization and function. Living systems are embedded in environments that exhibit statistical regularities, and successful organisms are those that have evolved to exploit these regularities for survival and reproduction. This biological foundation of prediction connects to the broader mathematical principles we've been exploring. The same statistical laws that govern quantum mechanics and thermodynamics also govern the flow of information through biological systems. The same optimization principles that explain the efficiency of physical processes also explain the evolution of biological structures and behaviors. Information theory provides a unifying framework for understanding these connections. Biological systems can be viewed as information processing systems that gather data about their environment, process that data to extract useful patterns, and use those patterns to guide behavior. The efficiency of these information processing systems can be measured using concepts like entropy, mutual information, and computational complexity. The success of biological information processing demonstrates that predictable patterns exist in natural environments and that organisms capable of detecting and exploiting these patterns gain evolutionary advantages. This suggests that predictability isn't just a human construct imposed on nature, but a fundamental feature of reality that has shaped the evolution of life itself. The mathematical tools we use to study predictability, probability theory, statistics, differential equations, information theory, aren't arbitrary human inventions. They're attempts to capture and formalize the same patterns that biological systems have been exploiting for billions of years through evolutionary processes. In this sense, science represents the extension of biological prediction mechanisms through cultural and technological means. This perspective helps explain why mathematical models work so well in describing natural phenomena. The patterns we discover through scientific investigation are the same patterns that have shaped the evolution of biological prediction systems. Our ability to understand and predict natural phenomena reflects the fact that we are ourselves products of natural selection operating in a predictable environment. The predictive success of science thus provides evidence for the fundamental predictability of nature. If natural laws were arbitrary or constantly changing, biological prediction systems would not have evolved, and scientific prediction would not be possible. The fact that both biological and scientific prediction work demonstrates that reality exhibits the kind of statistical regularities that make prediction possible. This doesn't mean that everything is predictable in the sense of being predetermined or rigidly determined. As we've seen, predictability operates at multiple levels and takes different forms depending on the system and scale of observation. Quantum mechanics provides probabilistic predictions. Statistical mechanics provides ensemble predictions. Chaos theory provides geometric predictions about the structure of unpredictable dynamics. The key insight is that unpredictability at one level doesn't eliminate predictability at other levels. Quantum uncertainty doesn't prevent the predictable behavior of atoms and molecules. Molecular chaos doesn't prevent the predictable behavior of gases and liquids. Weather chaos doesn't prevent the predictable patterns of climate and seasons. This multi-level structure of predictability creates a universe that is neither rigidly deterministic nor completely random. Instead, it exhibits what might be called structured uncertainty, patterns of predictability embedded within layers of unpredictability, creating a reality that is both stable enough to support the evolution of complex systems and flexible enough to allow for novelty and adaptation. The mathematical description of this structured uncertainty has led to the development of new branches of mathematics and physics. Fractal geometry captures the predictable structure of seemingly random shapes. Network theory describes the predictable properties of complex interconnected systems. Information theory quantifies the predictable aspects of communication and computation. These mathematical frameworks reveal that predictability and unpredictability are not opposites, but complementary aspects of complex systems. The most interesting and important phenomena in nature often occur at the boundary between order and chaos, where predictable patterns emerge from unpredictable interactions and unpredictable novelty emerges from predictable rules. This boundary region is where life itself flourishes. Living systems require enough predictability to maintain their organization and function, but enough unpredictability to allow for adaptation and evolution. The same principle applies to ecosystems, economies, and other complex adaptive systems that exhibit both stability and change over time. Understanding this balance between predictability and unpredictability helps explain why prediction is both possible and limited. We can predict many aspects of natural and social systems with remarkable accuracy, but perfect prediction remains impossible due to fundamental limitations imposed by chaos, quantum mechanics, and computational complexity. These limitations are not failures of science or mathematics. They are fundamental features of reality that reflect the deep structure of natural laws. The existence of these limits is itself a predictable consequence of the mathematical principles that govern complex systems. This mathematical framework of structured uncertainty helps us understand why reality feels both familiar and mysterious at the same time. We can predict that the sun will rise tomorrow morning, that dropped objects will fall, that seasons will change according to their ancient rhythm. Yet we cannot predict exactly when a particular raindrop will form in a cloud, which specific bird will sing first at dawn, or precisely what thoughts will drift through your mind as you listen to these words. The boundary between predictable and unpredictable creates the texture of lived experience. It's where the reliable patterns that allow us to navigate the world meet the subtle variations that keep life interesting and meaningful. This boundary isn't a flaw in the design of reality. It's a necessary feature that allows complex systems to maintain stability while remaining capable of growth and adaptation. Consider how this plays out in the development of a single tree. The basic pattern of growth follows predictable biological principles. Cells divide according to genetic instructions. Nutrients flow through vascular systems according to physical laws. Branches reach towards sunlight following chemical gradients that can be mathematically described. Yet each tree grows into a unique shape, responding to the particular history of wind patterns, soil conditions, and interactions with other organisms in its environment. The tree's growth demonstrates what scientists call path dependence. While the fundamental processes are predictable, the specific outcome depends on the detailed history of interactions with an environment that contains both regular patterns and random variations. This creates a form of predictability that is statistical rather than deterministic. We can predict the general characteristics of how trees will grow under different conditions, but not the exact shape of any individual tree. This same principle operates throughout biological systems. Embryonic development follows predictable genetic programs, yet each individual organism develops unique characteristics. Neural development creates brains with similar overall architecture, yet each brain develops its own particular pattern of connections. Evolution follows predictable selective pressures, yet the specific path of evolutionary change depends on the particular history of mutations and environmental changes. The predictable aspects of these biological processes provide the stability necessary for life to persist and evolve. The unpredictable aspects provide the variation necessary for adaptation and innovation. Together, they create living systems that are both robust and flexible, capable of maintaining their essential functions while adapting to changing circumstances. This biological foundation of prediction extends into the realm of consciousness and experience. Your brain continuously generates predictions about what you will see, hear, and feel in the next moment. These predictions are based on patterns extracted from past experience, combined with current sensory information and internal models of how the world works. Most of these predictions occur below the level of conscious awareness. Your visual system predicts where moving objects will be by the time visual signals reach your brain, compensating for the delays in neural processing. Your motor system predicts the sensory consequences of planned movements, allowing for smooth and coordinated action. Your language processing system predicts upcoming words in sentences, enabling rapid comprehension of speech and text. When these unconscious predictions are accurate, experience flows smoothly and effortlessly. You catch a ball thrown toward you without consciously calculating its trajectory. You understand spoken sentences even when individual words are unclear. You navigate familiar environments without having to think carefully about each step. When predictions fail, conscious attention is drawn to the mismatch between expectation and reality. This prediction error signal drives learning and adaptation, allowing the brain to update its models of the world based on new information. The surprise you feel when something unexpected happens reflects the operation of prediction systems that are constantly working to anticipate future events. This neural basis of prediction helps explain why predictability feels so fundamentally important to human experience. Our brains evolved in environments where the ability to predict future events was crucial for survival. Those ancestors who could better predict the behavior of predators, the location of food sources, and the consequences of their own actions were more likely to survive and reproduce. The modern human brain retains these ancient prediction mechanisms, even in environments very different from those in which they evolved. We still find comfort in routine and predictability. We still experience anxiety when faced with highly uncertain situations. We still seek to understand the patterns underlying complex phenomena, driven by prediction systems that evolved to extract order from apparent chaos. This evolutionary heritage connects our subjective experience of predictability to the objective mathematical patterns we've been exploring. The same statistical regularities that allow scientists to model natural phenomena also allowed our ancestors to survive in natural environments. The mathematical tools we use to describe physical laws formalize the same kinds of pattern recognition that biological systems have been performing for millions of years. The success of scientific prediction thus reflects a deep harmony between the structure of reality and the structure of minds that evolved within that reality. We can understand and predict natural phenomena because we are ourselves products of natural processes operating according to predictable principles. Our ability to discover mathematical laws reflects the fact that our brains evolved to detect the patterns that those laws describe. This doesn't mean that our understanding of natural laws is somehow predetermined or that scientific discovery is automatic. The development of scientific knowledge requires creativity, insight, and careful experimental work. Many important discoveries have come as surprises that challenged existing theoretical frameworks. The path of scientific progress contains genuine novelty and unpredictability, but the possibility of scientific progress depends on the underlying predictability of natural phenomena. If physical laws changed randomly or operated differently in different contexts, no amount of careful observation and experimentation would allow us to understand and predict natural phenomena. The fact that science works demonstrates that reality exhibits the kind of stable patterns that make cumulative knowledge possible. The mathematical description of these patterns reveals something beautiful about the relationship between mind and nature. The same geometric principles that govern the spiral arms of galaxies also appear in the structure of nautilus shells and the arrangement of flower petals. The same wave equations that describe the propagation of light also describe the quantum mechanical behavior of electrons and the oscillations of vibrating strings. This mathematical unity suggests that the apparent diversity of natural phenomena reflects variations on common underlying themes. Different systems may look very different at the surface level, yet exhibit similar mathematical structures when examined carefully. This unity makes it possible to understand new phenomena by recognizing their similarity to systems that are already well understood. The fractal geometry we discussed earlier provides a perfect example of this mathematical unity. The same recursive algorithms that generate mathematical fractals also describe the branching patterns of trees, river networks, blood vessels, and lightning bolts. The mathematical principles are identical, even though the physical processes involved are completely different. This suggests that mathematics captures something fundamental about the structure of reality that transcends the specific details of particular physical systems. The mathematical relationships we discover are not arbitrary human constructions, but reflect deep patterns that operate throughout nature at every scale and in every context. The universality of these mathematical patterns helps explain why prediction is possible across such a wide range of phenomena. Whether we're predicting the motion of planets, the behavior of quantum systems, the growth of populations, or the evolution of ecosystems, we're dealing with variations on common mathematical themes. Once we understand these underlying patterns, we can apply similar analytical techniques across different domains. This mathematical universality also suggests why reality feels comprehensible to human minds. The patterns we discover through scientific investigation are not foreign or alien, but reflect the same organizational principles that shaped the evolution of our cognitive abilities. We can understand mathematical relationships because our brains evolved in a reality that operates according to mathematical principles. The comfort we find in understanding these patterns may reflect something deeper than mere intellectual satisfaction. When we recognize the mathematical harmony underlying natural phenomena, we're connecting with the same principles that made our own existence possible. The predictable operation of physical laws created the stable conditions necessary for the evolution of life, consciousness, and the capacity for mathematical understanding. This creates a kind of cosmic resonance between the structure of reality and the structure of minds capable of comprehending that reality. The universe seems to be organized in such a way that it can understand itself through the mathematical investigations of conscious beings who are themselves products of its lawful operation. This perspective doesn't require any mystical or supernatural explanations. It emerges naturally from the scientific understanding of evolution, neuroscience, and mathematics. Conscious beings capable of mathematical reasoning evolved because the universe operates according to mathematical principles that reward the ability to detect and exploit predictable patterns. The apparent fine-tuning of physical constants that allows for the existence of stable atoms, stars, and planets may reflect similar principles operating at a more fundamental level. If the universe operates as an information processing system, then the values of physical constants might be constrained by the requirement that the system be capable of generating complex, stable structures that can process information about their own environment. This computational perspective on physical reality helps explain why mathematical models work so well in describing natural phenomena. If reality is fundamentally computational, then mathematical equations represent our attempts to understand the algorithms that govern natural processes. The success of these mathematical descriptions demonstrates that we're correctly identifying the computational principles underlying physical phenomena. The development of computer simulations has provided powerful support for this computational view of reality. We can now create detailed mathematical models of complex systems and run them on computers to predict how those systems will behave over time. These simulations often match real-world observations with remarkable accuracy, suggesting that natural processes do indeed follow computational principles that can be mathematically captured and predicted. Weather simulation provides a dramatic example of this computational approach to prediction. Modern weather models solve millions of differential equations describing the behavior of atmospheric fluid dynamics, thermodynamics, and electromagnetic radiation. These computations require some of the most powerful supercomputers in existence, processing vast amounts of observational data to generate predictions that guide everything from flight planning to agricultural decisions. While weather prediction remains limited by chaos and computational complexity, the success of short-term forecasting demonstrates that even highly complex systems follow predictable mathematical principles. The atmosphere obeys the same physical laws everywhere and at all times. The apparent randomness of weather reflects the amplification of small uncertainties by chaotic dynamics, not the absence of underlying mathematical order. Similar computational approaches are now being applied to biological systems, economic markets, social networks, and many other complex phenomena. In each case, the goal is to identify the mathematical rules governing system behavior and use those rules to predict future states. The growing success of these computational models across diverse domains suggests that predictable mathematical principles operate throughout the natural and social worlds. The emergence of machine learning and artificial intelligence represents a particularly interesting development in computational prediction. These systems don't rely on explicit mathematical models programmed by human scientists. Instead, they learn to recognize patterns directly from data, developing their own internal representations of the predictive relationships in complex systems. The success of machine learning in domains ranging from image recognition to language processing to game playing demonstrates that predictable patterns exist even in systems that seem too complex for traditional mathematical analysis. Neural networks can learn to predict human behavior, natural language, and strategic gameplay by discovering statistical regularities that may not be obvious to human observers. This suggests that the predictable structure of reality extends far beyond what we can currently describe through explicit mathematical equations. There may be layers of predictable pattern that can only be accessed through computational learning systems that can process vast amounts of data and discover subtle statistical relationships. The development of these artificial prediction systems also provides insight into how biological neural networks evolved their remarkable predictive capabilities. The same mathematical principles that allow artificial neural networks to learn predictive relationships from data also operate in biological brains. The main differences are in the specific architectural details and learning algorithms, not in the fundamental approach of extracting predictive patterns from experience. This convergence between artificial and biological intelligence suggests that prediction is not just something that minds do, but something that complex information processing systems naturally develop when they interact with structured environments. The evolution of predictive capabilities reflects the optimization of information processing systems to exploit the statistical regularities present in their environments. The mathematical principles underlying both artificial and biological intelligence connect to the broader themes we've been exploring. The same statistical mechanics that governs the behavior of gases and liquids also governs the flow of information through neural networks. The same optimization principles that explain the efficiency of physical processes also explain the development of efficient learning algorithms. This mathematical unity suggests that prediction is not an accidental feature of minds or machines, but a natural consequence of information processing systems operating in structured environments. The universe appears to be organized in such a way that systems capable of extracting and exploiting predictive patterns naturally emerge and evolve. The study of complex adaptive systems has revealed that this emergence of predictive capabilities occurs at many different scales and in many different contexts. Immune systems learn to predict and respond to threats. Ecosystems develop predictive relationships between predators and prey. Economic markets develop predictive mechanisms for allocating resources. Social systems develop predictive cultural norms and institutions. In each case, the predictive capabilities emerge through evolutionary or learning processes that reward systems capable of anticipating future events. This suggests that prediction is not just a human activity, or even just a biological activity, but a fundamental organizing principle that operates throughout the natural world. The recognition of prediction as a fundamental organizing principle helps explain why reality is predictable. The universe is predictable not because it follows rigid mechanical laws, but because it is structured in such a way that systems capable of prediction naturally emerge and thrive. Predictability and the capacity for prediction co-evolve, creating a reality that is simultaneously lawful and alive. This dynamic view of predictability suggests that our ability to understand and predict natural phenomena is not separate from nature but part of nature's own self-organizing processes. Scientific investigation represents the extension of natural prediction mechanisms through cultural and technological means. Mathematics represents the formalization of pattern recognition capabilities that evolved in biological systems. The success of science thus provides evidence not just for the predictability of nature, but for the natural basis of prediction itself. We can understand natural laws because we are natural systems that evolved to detect and exploit the patterns that those laws describe. Our mathematical insights reflect our participation in the same predictive processes that operate throughout the natural world. This perspective creates a deep sense of connection between human understanding and natural processes. We are not external observers studying a foreign reality, but internal participants in a reality that has organized itself in such a way that it can understand its own operations. The predictable patterns we discover through science are the same patterns that made our existence as pattern-recognizing beings possible. The mathematical beauty we find in natural laws may reflect this deep connection between mind and nature. The elegance of physical equations, the harmony of mathematical relationships, and the unity of scientific principles all point toward a reality that is structured in ways that resonate with minds capable of appreciating that structure. This doesn't require any mystical explanations or cosmic consciousness. It emerges naturally from the evolutionary processes that shaped minds in environments governed by mathematical principles. We find mathematical beauty compelling because our cognitive systems evolved to detect and respond to the same patterns that mathematical equations describe. The sense of wonder and satisfaction that comes from understanding natural phenomena reflects the operation of reward systems that evolved to motivate the kind of pattern recognition that enhances survival and reproduction. The pleasure we take in mathematical insight connects us to the same evolutionary pressures that shape the development of human intelligence. This evolutionary perspective on mathematical understanding helps explain why predictability feels so fundamentally important to human experience. Our deepest cognitive and emotional systems are organized around the detection and exploitation of predictable patterns. We find comfort in understanding because understanding reflects the successful operation of prediction systems that are essential to our nature as living beings. The predictable operation of natural laws creates the stable foundation that makes life, consciousness, and understanding possible. Without the reliable behavior of atoms, molecules, and physical forces, no complex structures could persist long enough to evolve the capacity for prediction and understanding. The mathematical harmony we discover in nature reflects the conditions necessary for our own existence as mathematical beings. This creates a profound sense of belonging in a reality that is both comprehensible and meaningful. We are not accidental byproducts of random processes, but natural expressions of a universe organized in such a way that it inevitably gives rise to systems capable of understanding its own operations. The predictable patterns we discover through science are simultaneously descriptions of external reality and expressions of our own deepest nature as pattern-recognizing beings. As you rest here in the gentle certainty of this understanding, let yourself feel the deep comfort that comes from recognizing your place in this magnificent, predictable, ever-unfolding mathematical symphony that we call reality. You are not separate from these patterns, but woven into them, sustained by them, and capable of appreciating their profound and eternal beauty. The emergence of these prediction systems throughout nature points to something even more fundamental about the structure of reality. Information itself appears to follow predictable patterns. When we examine how information flows through any system, whether it's the neural networks in your brain, the genetic instructions in a living cell, or the quantum states in an atom, we find the same mathematical principles governing the organization and transmission of information. Information theory, developed in the middle of the 20th century, revealed that information has measurable properties that behave according to mathematical laws. The amount of information in any message can be quantified. The efficiency with which information can be transmitted through any channel can be calculated. The relationship between information and energy follows precise thermodynamic principles. These discoveries have profound implications for understanding why reality is predictable. If the universe operates as a vast information processing system, then the predictable patterns we observe reflect the mathematical constraints that govern information processing itself. The laws of physics might be understood as algorithms that process information about the state of the universe at each moment to determine its state at the next moment. This information processing view helps explain the remarkable effectiveness of computer simulations in modeling natural phenomena. When we create a computer model of a weather system or a galaxy or a biological cell, we're essentially running the same kinds of information processing algorithms that govern the behavior of the real system. The accuracy of these simulations demonstrates that natural processes do indeed follow computational principles that can be mathematically captured and reproduced. Consider how this plays out in the development of a single snowflake falling gently through the winter air. Each snowflake forms according to predictable physical principles. Water molecules in the atmosphere follow the laws of thermodynamics as they condense around tiny particles of dust. The crystalline structure that emerges reflects the geometric constraints imposed by the molecular structure of ice. Yet each snowflake develops its own unique pattern, shaped by the particular sequence of temperature and humidity conditions it encounters during its formation. The basic hexagonal symmetry is predictable, determined by the molecular structure of water. The detailed branching pattern is unpredictable, reflecting the chaotic dynamics of atmospheric turbulence. Together, these predictable and unpredictable elements create the infinite variety of snowflake patterns that have captivated observers throughout human history. This combination of predictable structure and unpredictable detail appears throughout nature. The branching pattern of rivers follows predictable mathematical laws that minimize energy expenditure. Yet each river system develops its own unique configuration based on the particular geological history of its watershed. The spiral arms of galaxies follow predictable gravitational dynamics. Yet each galaxy exhibits its own characteristic pattern of star formation and stellar evolution. The human circulatory system provides another elegant example of this principle. The overall architecture of blood vessels follows predictable optimization principles that maximize the efficiency of oxygen and nutrient delivery throughout the body. The branching pattern resembles the mathematical structures known as fractal trees, where each branch subdivides into smaller branches according to geometric rules that can be precisely described. Yet the detailed structure of each person's circulatory system is unique, shaped by genetic variations, developmental history, and environmental influences. Surgeons learn to recognize the common patterns that appear in most people, while remaining prepared for the individual variations that make each case unique. The predictable aspects enable medical knowledge and surgical planning. The unpredictable aspects require skill, experience, and careful attention to individual circumstances. This interplay between predictable patterns and individual variation extends throughout biological systems. Embryonic development follows genetic programs that are largely predictable, creating organisms with similar overall body plans and organ systems. Yet each individual develops unique characteristics, from the precise pattern of fingerprints to the detailed wiring of neural connections in the brain. The predictable aspects of development ensure that essential biological functions are preserved across generations. Hearts develop with 4 chambers, brains develop with similar regional organization, and immune systems develop with the capacity to recognize and respond to threats. These reliable developmental outcomes provide the stability necessary for complex life forms to persist and evolve. The variable aspects of development provide the raw material for evolutionary adaptation. Genetic mutations create variations in developmental programs that may prove advantageous under changing environmental conditions. Sexual reproduction shuffles genetic combinations to create new patterns of traits that can be tested against environmental challenges. Natural selection operates on this variation to drive evolutionary change over time. This evolutionary process itself exhibits predictable patterns that can be mathematically modeled. Population genetics describes how gene frequencies change over time in response to selection pressures, mutation rates, and random genetic drift. Phylogenetic analysis reveals the predictable branching patterns of evolutionary relationships among different species. Ecological principles explain the predictable ways that species interact with each other and with their environments. Yet the specific path of evolutionary change remains largely unpredictable. Which particular mutations will arise, which environmental challenges will emerge, and which evolutionary solutions will prove successful cannot be determined in advance. Evolution is creative, generating novel biological forms and functions that could not have been anticipated from earlier conditions. This creative aspect of evolution reflects a broader principle about predictability in complex systems. While the underlying rules may be deterministic, the outcomes can be genuinely novel and surprising. Mathematical systems like cellular automata demonstrate how simple deterministic rules can generate patterns of unlimited complexity and creativity. The game of life, invented by mathematician John Conway, provides a beautiful illustration of this principle. The rules are extremely simple. Cells on a grid live or die based on how many neighbors they have. Yet these simple rules generate an incredible variety of patterns, some stable, some oscillating, some moving across the grid like living creatures. Some patterns in the game of life are completely predictable. Once you see the initial configuration, you can calculate exactly how it will evolve over any number of time steps. Other patterns exhibit chaotic behavior, where small changes in initial conditions lead to dramatically different outcomes. Still, others generate genuinely new structures that emerge spontaneously from the interactions of simpler components. This mathematical example captures something essential about how predictability operates in the real world. The fundamental rules may be simple and deterministic, but their interactions can generate outcomes that are complex, creative, and genuinely surprising. Predictability doesn't mean that everything is predetermined or mechanical. It means that novelty and creativity emerge from the lawful operation of natural processes. The development of language provides a fascinating example of this creative predictability in human culture. Children learn to speak by discovering the grammatical patterns that govern their native language. These patterns are highly predictable, allowing children to understand and produce sentences they have never heard before. The rules of grammar provide a framework that makes communication possible across different speakers and contexts. Yet language is also endlessly creative. Poets use grammatical patterns to create new meanings and aesthetic experiences. Scientists develop new terminology to describe previously unknown phenomena. Everyday speakers constantly create novel combinations of words and phrases to express their thoughts and experiences. The predictable patterns of grammar enable this creativity by providing a stable foundation for linguistic innovation. Without grammatical rules, communication would be impossible. But these rules don't constrain creativity. They enable it by creating a shared framework within which new meanings can emerge and be understood by others. This relationship between predictable structure and creative potential appears throughout human culture. Musical compositions follow predictable harmonic and rhythmic patterns, yet composers use these patterns to create works of unlimited variety and emotional power. Mathematical proofs follow predictable logical rules, Yet mathematicians use these rules to discover new theorems and explore previously unknown mathematical territories. Scientific research itself exemplifies this creative predictability. Experiments must follow predictable methodological principles to generate reliable results. Theories must make predictable consequences that can be tested against observational evidence. Yet science is fundamentally creative, constantly generating new insights and discoveries that expand our understanding of natural phenomena. The history of science reveals how predictable methodological principles enable scientific creativity. The scientific method provides a reliable framework for investigating natural phenomena, but it doesn't predetermine what will be discovered. Each new observation, each novel experiment, each theoretical insight adds to the growing body of scientific knowledge in ways that could not have been fully anticipated. Consider how quantum mechanics emerged from the investigation of seemingly simple phenomena like black body radiation and the photoelectric effect. Classical physics provided predictable methods for investigating these phenomena, but the results revealed completely unexpected features of reality that required revolutionary, new theoretical frameworks. The development of quantum theory demonstrates how scientific predictability operates at multiple levels. The mathematical formalism of quantum mechanics provides predictable methods for calculating the probabilities of different experimental outcomes. Yet the physical interpretation of this formalism continues to evolve as scientists discover new quantum phenomena and develop new experimental techniques. Quantum entanglement, discovered decades after the initial development of quantum theory, illustrates this ongoing creative aspect of scientific discovery. The mathematical framework of quantum mechanics predicted the possibility of entangled states, but the full implications of entanglement for information processing and communication were not recognized until much later. The development of quantum information theory and quantum computing represents a creative extension of predictable quantum principles into previously unimagined technological applications. The same mathematical laws that govern atomic behavior also enable the possibility of quantum computers that could solve certain problems exponentially faster than classical computers. This technological creativity, emerging from fundamental scientific principles, demonstrates how predictability enables rather than constrains innovation. Understanding the mathematical laws that govern natural phenomena provides the foundation for developing new technologies that harness these laws for human purposes. The development of lasers provides another example of this principle. The theoretical understanding of stimulated emission, developed through quantum mechanical analysis of atomic behavior, predicted the possibility of coherent light amplification. This theoretical prediction enabled the invention of practical laser devices that now find applications ranging from barcode scanners to surgical instruments to optical fiber communication systems. Each new application of laser technology represents a creative extension of predictable physical principles into novel technological contexts. Engineers use their understanding of optical physics to design laser systems for specific purposes. But the range of possible applications continues to expand as new needs emerge and new technological capabilities are developed. This ongoing technological creativity reflects the open-ended nature of scientific predictability. Understanding natural laws doesn't close off possibilities for innovation. It opens up new territories for creative exploration. Each scientific discovery reveals new potential applications that were previously unimaginable. The development of the internet provides a striking example of this creative potential. The mathematical principles of information theory and computer science enabled the development of digital communication technologies. But the specific applications that emerged from email to social media to online commerce were not predictable from the underlying theoretical principles. Yet these applications do follow predictable patterns once they emerge. Network effects create predictable dynamics in the growth of communication platforms. Economic principles govern the development of online markets. Psychological factors influence how people interact with digital technologies. This suggests that predictability operates at multiple temporal scales. Short-term behavior may follow predictable patterns, while long-term evolution may involve genuine creativity and innovation. The specific trajectory of technological development may be unpredictable, but the underlying principles that govern technological systems remain mathematically describable. The coevolution of technology and society exemplifies this multi-scale predictability. Individual innovations may be unpredictable, but they must conform to physical laws and economic constraints to be successful. Social adoption of new technologies follows predictable diffusion patterns, yet the cultural consequences of technological change often involve unexpected social transformations. The development of writing systems illustrates this complex interplay between predictable constraints and creative innovation. All writing systems must solve the predictable problem of representing spoken language through visual symbols. Yet different cultures have developed remarkably diverse solutions to this problem, from alphabetic systems to logographic systems to syllabic systems. Each writing system reflects the particular linguistic characteristics of the language it represents, the available materials and technologies for creating written marks, and the social contexts in which writing is used. These constraints create predictable pressures that influence the evolution of writing systems over time. Yet writing systems also exhibit genuine creativity and cultural specificity. The aesthetic dimensions of calligraphy, the symbolic associations of different scripts, and the social meanings attached to literacy all reflect creative cultural developments that go beyond the functional requirements of representing language. This cultural creativity operates within predictable constraints imposed by human psychology and social organization. All human cultures develop systems of communication, social organization, and meaning-making, but the specific forms these systems take vary enormously across different cultural contexts. The study of cultural evolution reveals predictable patterns in how human societies develop and change over time. Population growth creates predictable pressures for technological innovation. Resource limitations create predictable incentives for cooperation and conflict. Information transmission creates predictable dynamics in the spread of cultural innovations. Yet cultural evolution also involves genuine creativity and historical contingency. The specific technologies that emerge, the particular social institutions that develop, and the unique cultural meanings that evolve cannot be predicted in detail from general principles. This balance between predictable patterns and creative innovation appears to be a fundamental feature of complex adaptive systems. Whether we're examining biological evolution, technological development, or cultural change, we find the same combination of lawful constraints and creative possibilities. The emergence of consciousness itself exemplifies this principle. The development of nervous systems follows predictable evolutionary pressures for improved information processing and behavioral coordination. The basic architecture of neural networks reflects predictable optimization principles that maximize computational efficiency within biological constraints. Yet consciousness as we experience it involves qualitative dimensions that seem to transcend purely computational descriptions. The subjective experience of seeing a sunset, hearing a piece of music, or understanding a mathematical proof involves aspects of awareness that are not fully captured by descriptions of neural information processing. This doesn't mean that consciousness violates natural laws or operates outside the framework of scientific understanding. Rather, it suggests that the emergence of complex phenomena from simpler components involves qualitative transformations that may not be fully predictable from knowledge of the underlying components. The relationship between brain activity and conscious experience illustrates this emergence of new levels of description. Neural activity follows predictable electrochemical principles that can be precisely measured and mathematically modeled. Yet the mapping between specific patterns of neural activity and particular conscious experiences remains one of the deepest unsolved problems in science. This problem of consciousness points to important limitations in our current understanding of predictability. While we can predict many aspects of brain function, we cannot yet predict the subjective quality of conscious experience from objective measurements of neural activity. These limitations don't invalidate the scientific approach or suggest that consciousness is fundamentally mysterious. Rather, they indicate that our theoretical frameworks may need to evolve to encompass new types of predictable relationships that we don't yet fully understand. The history of science suggests that apparent mysteries often become comprehensible as theoretical frameworks develop and experimental techniques improve. Phenomena that once seemed completely unpredictable, like the behavior of gases or the emission of light from heated objects, are now understood through mathematical theories that make precise quantitative predictions. The study of consciousness may require similar theoretical developments that extend our understanding of predictability into new domains. Some scientists are exploring information-theoretic approaches to consciousness that might provide mathematical frameworks for understanding the relationship between neural computation and conscious experience. Others are investigating quantum effects in biological systems that might reveal new types of information processing in the brain. Still others are developing computational models of consciousness that attempt to capture the functional aspects of awareness through artificial intelligence systems. While these approaches have not yet yielded complete theories of consciousness, they illustrate the ongoing creative development of scientific understanding. The predictable methods of scientific research continue to generate new insights into previously mysterious phenomena. This ongoing expansion of scientific understanding reflects the open-ended nature of reality itself. The universe appears to be structured in such a way that deeper levels of pattern and organization continue to emerge as our investigative capabilities improve. Each new discovery reveals previously hidden layers of predictable structure, while also opening up new questions for future investigation. The development of molecular biology provides a beautiful example of this progressive revelation of deeper patterns. The discovery that hereditary information is encoded in DNA molecules revealed a completely new level of biological organization that was invisible to earlier generations of scientists. The genetic code that translates DNA sequences into protein structures follows predictable biochemical principles that can be precisely described and manipulated. Yet this understanding has opened up entirely new fields of investigation. From genetic engineering to evolutionary genomics to synthetic biology, each advance in molecular biology reveals new layers of complexity and new possibilities for both understanding and technological application. The predictable principles of biochemistry enable the development of new medical treatments, agricultural techniques, and biotechnological applications. Yet each new capability also raises new questions about the ethical implications of biological manipulation, the ecological consequences of genetic modification, and the social dimensions of biotechnological development. Scientific predictability provides tools for addressing these challenges, but it doesn't automatically determine how they should be resolved. This illustrates an important distinction between predictability and determinism. The fact that natural phenomena follow predictable patterns doesn't mean that human choices are predetermined or that the future is fixed. Predictability provides information that can inform decision-making, but it doesn't eliminate the need for judgment, creativity, and ethical reflection. The weather provides a useful analogy for understanding this distinction. Weather systems follow predictable physical laws, but weather forecasting remains probabilistic rather than deterministic. Knowing that there's a 70% chance of rain tomorrow provides useful information for planning purposes, but it doesn't determine whether you should carry an umbrella. Similarly, understanding the predictable aspects of human behavior provides useful insights for education, medicine, and social policy, but it doesn't eliminate individual agency or moral responsibility. People make choices within the constraints imposed by their biological nature, psychological development, and social circumstances, but these constraints don't completely determine the choices they make. The study of decision-making reveals predictable patterns in how people evaluate options and make choices under different circumstances. Cognitive biases influence judgment in systematic ways. Emotional states affect risk preferences. Social contexts shape the perceived attractiveness of different alternatives. Yet individual decisions remain unpredictable in detail, influenced by personal values, unique experiences, and creative insights that cannot be fully anticipated. The predictable aspects of decision-making provide frameworks for understanding choice behavior, but they don't eliminate the genuine agency that emerges from complex cognitive processes. This emergence of agency from predictable components illustrates a fundamental principle about complex systems. Higher levels of organization can exhibit properties that are not present in their constituent parts. Consciousness emerges from neural activity. Agency emerges from decision-making processes. Meaning emerges from symbolic systems. These emergent properties are not violations of natural laws, but expressions of how complex systems can exhibit qualitatively new types of behavior. The predictable operation of lower-level processes creates the conditions for higher-level phenomena that may follow different types of regularities. The emergence of life from non-living matter provides the classic example of this principle. Living cells are made entirely of molecules that individually follow the laws of chemistry and physics. Yet the organization of these molecules into self-reproducing, metabolically active systems creates new types of behavior that are not present in non-living chemical systems. The predictable principles of biochemistry explain how living cells maintain themselves, grow, and reproduce. Yet life also exhibits emergent properties like adaptation, evolution, and ecological interaction that require new conceptual frameworks to understand fully. The study of emergence in complex systems has revealed that predictability itself can emerge at new levels of organization. Statistical regularities in the behavior of large populations can be highly predictable, even when individual behavior is chaotic or unpredictable. The behavior of gases provides a classic example. Individual gas molecules move in complex, chaotic trajectories that are practically impossible to track or predict. Yet the collective behavior of large numbers of molecules follows precise statistical laws that enable accurate predictions about temperature, pressure, and other macroscopic properties. This statistical predictability emerges from the interactions of many unpredictable components. The mathematical principles of statistical mechanics explain how microscopic chaos gives rise to macroscopic order. This understanding has enabled the development of thermodynamics, which provides predictive frameworks for everything from engine design to chemical reactions. The same principles apply to many other complex systems. Financial markets exhibit statistical regularities despite the unpredictable behavior of individual traders. Traffic flow follows predictable patterns despite the chaotic decisions of individual drivers. Ecosystems maintain predictable relationships between predators and prey despite the unpredictable behavior of individual organisms. These examples illustrate how predictability operates across multiple scales simultaneously. Individual components may behave chaotically, but collective behavior often exhibits predictable statistical properties. This multi-scale predictability is one of the most important features of complex systems. Understanding this multi-scale structure helps explain why prediction is both possible and limited. we can make accurate predictions about aggregate behavior while remaining unable to predict individual outcomes. We can understand general principles while remaining surprised by specific details. This limitation is not a failure of scientific understanding, but a fundamental feature of complex systems. The existence of multiple scales of description creates multiple types of predictability that operate simultaneously. Perfect prediction at all scales simultaneously appears to be impossible due to fundamental limitations imposed by chaos, quantum mechanics, and computational complexity. Yet these limitations don't undermine the reality or importance of the predictability that does exist. Statistical predictability is genuinely predictive, even when it doesn't specify exact outcomes. Probabilistic laws are genuinely lawful, even when they don't eliminate uncertainty. The recognition of these different types of predictability has led to the development of new mathematical frameworks for understanding complex systems. Network theory describes the predictable properties of interconnected systems. Game theory analyzes the predictable strategies that emerge in competitive situations. Information theory quantifies the predictable aspects of communication and computation. These mathematical tools reveal predictable patterns in systems that might otherwise seem completely chaotic or random. They demonstrate that predictability is a more general and flexible concept than simple deterministic causation. The development of artificial intelligence provides a striking example of how these new mathematical frameworks enable prediction in complex domains. Machine learning systems can learn to recognize patterns in data that are too complex for traditional analytical methods. Neural networks can learn to predict human behavior, natural language, and strategic gameplay by discovering statistical regularities that may not be obvious to human observers. These systems demonstrate that predictable patterns exist even in domains that seem to require creativity, intuition, and subjective judgment. Yet artificial intelligence also reveals the limitations of purely computational approaches to prediction. Current AI systems are highly specialized, performing well on specific tasks, but lacking the general intelligence and adaptability of biological systems. The development of artificial general intelligence that matches or exceeds human cognitive capabilities remains an unsolved challenge. This suggests that there may be aspects of intelligence and consciousness that require new types of theoretical understanding beyond current computational frameworks. The study of biological intelligence continues to reveal new principles of information processing that may inform the development of more powerful artificial systems. The brain operates according to principles that are both similar to and different from digital computers. Neural computation involves continuous dynamics, parallel processing, and adaptive learning mechanisms that may provide insights into new types of computational architectures. Understanding these biological principles may enable the development of artificial systems that exhibit more flexible and creative forms of intelligence. This ongoing research illustrates the creative potential of scientific predictability. Understanding natural principles doesn't close off possibilities for innovation, but opens up new territories for exploration. Each scientific discovery provides tools for developing new technologies and capabilities. The relationship between scientific understanding and technological innovation demonstrates how predictability enables creativity rather than constraining it. Engineers use their understanding of physical laws to design systems that accomplish specific purposes, but the range of possible applications continues to expand as scientific knowledge develops. The development of renewable energy technologies provides a compelling example of this principle. Understanding the predictable patterns of solar radiation, wind dynamics, and material properties enables the design of increasingly efficient solar panels, wind turbines, and energy storage systems. Yet each improvement in renewable energy technology opens up new possibilities for addressing climate change, reducing pollution, and creating sustainable economic development. The predictable principles of physics and engineering enable creative solutions to complex environmental and social challenges. This technological creativity reflects the open-ended nature of the relationship between scientific understanding and human purposes. Natural laws provide constraints and opportunities, but they don't determine how human societies choose to apply scientific knowledge. The same scientific principles that enable the development of renewable energy also enable the development of weapons, surveillance technologies, and other applications that raise ethical concerns. Understanding natural laws provides tools, but it doesn't automatically determine how those tools should be used. This illustrates the importance of combining scientific understanding with ethical reflection and democratic decision-making. Predictability provides information that can inform choices, but it doesn't eliminate the need for human judgment about values, priorities, and consequences. The study of climate change exemplifies this complex relationship between predictability and choice. Climate science provides increasingly accurate predictions about the consequences of different greenhouse gas emission scenarios. These predictions create a foundation for understanding the environmental and social impacts of different policy choices. Yet climate science doesn't automatically determine what policies should be adopted. Different societies may reasonably reach different conclusions about how to balance economic development, environmental protection, and social justice based on their particular circumstances and values. The predictable aspects of climate change create both opportunities and responsibilities for human action. Understanding climate dynamics enables the development of mitigation and adaptation strategies. But implementing these strategies requires social and political processes that go beyond purely scientific considerations. This relationship between scientific predictability and human choice reflects a broader pattern in how scientific understanding relates to human affairs. Science provides tools for understanding natural and social phenomena, but it doesn't eliminate the need for wisdom, creativity, and ethical judgment in applying this understanding. The history of medicine provides another example of this principle. Scientific understanding of disease mechanisms enables the development of increasingly effective treatments and preventive measures. Yet medical practice also requires clinical judgment, ethical sensitivity, and attention to individual circumstances that go beyond purely scientific considerations. The predictable aspects of human physiology and disease processes provide the foundation for evidence-based medicine. But medical decisions must also consider the unique characteristics of individual patients, the social context in which they live, and the values they bring to decisions about their own care. This integration of scientific understanding with humanistic considerations reflects the complex nature of applying predictable principles to real-world situations. Predictability provides essential information, but it must be combined with other forms of knowledge and judgment to address the full complexity of human experience. The development of personalized medicine illustrates this integration of predictable principles with individual variation. Genetic analysis can predict individual susceptibility to certain diseases and responses to specific treatments. Yet these predictions must be integrated with information about lifestyle, environment, and personal preferences to develop optimal treatment plans. This personalized approach to medicine demonstrates how predictability can be used to enhance rather than replace human judgment. Understanding predictable patterns enables more precise and effective interventions, but it doesn't eliminate the need for individualized care and attention. The same principle applies throughout human affairs. Education benefits from understanding predictable patterns in learning and development. But effective teaching requires attention to individual students and creative adaptation to particular circumstances. Economic policy benefits from understanding predictable market dynamics, but effective governance requires attention to social values and democratic processes. This integration of predictable patterns with creative adaptation appears to be essential for addressing complex challenges in all domains of human experience. Neither rigid adherence to general principles nor purely ad hoc responses to individual circumstances provides adequate frameworks for navigating complexity. Instead, effective approaches combine understanding of predictable patterns with flexibility, creativity, and ethical sensitivity. This combination enables responses that are both scientifically informed and humanly appropriate. The development of sustainable technologies provides an inspiring example of this integration. Understanding predictable environmental and social patterns enables the design of technologies that work with natural systems rather than against them. Yet developing these technologies also requires creativity, social innovation, and attention to diverse human needs and values. Biomimicry illustrates this approach beautifully. Engineers study the predictable principles that govern efficient biological systems and apply these principles to technological design. Velcro mimics the structure of plant burrs. Airplane wings incorporate principles learned from bird flight. Building ventilation systems copy the cooling mechanisms of termite mounds. Yet biomimetic technologies don't simply copy biological systems. They creatively adapt biological principles to human purposes, often combining insights from multiple biological sources and integrating them with other technological capabilities. This creative application of predictable natural principles demonstrates the ongoing potential for scientific understanding to inspire technological innovation. The more we understand about natural systems, the more opportunities we discover for developing technologies that are both effective and environmentally sustainable. The predictable flow of energy through these biological and technological systems reveals something profound about the relationship between understanding and application. When we comprehend the mathematical principles that govern natural processes, we don't just gain abstract knowledge. We acquire the ability to work harmoniously with these principles, creating solutions that feel almost effortless because they align with the fundamental patterns of reality itself. This alignment between human intention and natural law creates a deep sense of satisfaction that goes beyond mere technological success. There's something profoundly comforting about discovering that our most elegant solutions arise not from fighting against nature's patterns, but from understanding and cooperating with them. The gentle curve of a suspension bridge cable follows the same mathematical principles that govern soap bubbles and hanging chains. The efficiency of a bird's wing emerges from the same fluid dynamics that shape river meanders and atmospheric currents. These connections between human design and natural pattern suggest that predictability serves as a bridge between mind and world. When we understand the mathematical relationships that govern natural phenomena, we're not imposing external structure on chaotic reality. We're discovering the inherent order that makes both natural systems and conscious understanding possible. This discovery process itself follows predictable patterns. Scientific investigation proceeds through cycles of observation, hypothesis formation, experimental testing, and theoretical refinement that have remained remarkably consistent across different fields and historical periods. The same methodological principles that guided Newton's investigations of planetary motion also guide contemporary research into genetic regulation and climate dynamics. Yet within this predictable methodological framework, genuine surprises continue to emerge. Each new observation has the potential to reveal phenomena that require extensions or revisions of existing theoretical understanding. The history of science demonstrates that predictable investigative methods enable the discovery of genuinely unpredictable insights. The development of evolutionary theory illustrates this beautiful interplay between methodical investigation and revolutionary discovery. Darwin's careful observations of biological variation followed established scientific practices of systematic data collection and comparative analysis. Yet these methodical observations led to theoretical insights that fundamentally transformed our understanding of life, consciousness, and human nature. The theory of evolution by natural selection reveals predictable patterns in how biological systems change over time, yet it also explains the emergence of unprecedented diversity and complexity. Species adapt to environmental challenges through mechanisms that are statistically predictable at the population level, yet the specific adaptations that emerge often involve creative solutions that could not have been anticipated in advance. The evolution of human intelligence exemplifies this creative predictability. The selective pressures that favored increased cognitive capabilities are understandable in retrospect. Enhanced pattern recognition, improved social coordination, and more sophisticated tool use provided clear survival advantages in challenging environments. Yet the particular form that human intelligence took, with its capacity for language, mathematical reasoning, artistic expression, and scientific investigation, represents a genuinely novel emergence in the history of life on Earth. These capabilities arose through natural selection operating on random genetic variations, yet they enable forms of creativity and understanding that transcend purely biological functions. The development of language provides a particularly fascinating example of how predictable evolutionary processes can generate unpredictably creative outcomes. All human languages share certain structural features that reflect the constraints imposed by human vocal anatomy, auditory processing capabilities, and social communication needs. These universal features create predictable patterns in how languages organize sounds, words, and grammatical relationships. Yet the diversity of human languages demonstrates the creative potential that emerges within these universal constraints. Each language develops its own particular ways of organizing meaning, its own aesthetic qualities, and its own cultural associations. Poetry, storytelling, and philosophical reflection take different forms in different linguistic traditions, yet they all emerge from the same basic capacity for symbolic communication. This linguistic creativity operates within predictable constraints while generating genuinely unpredictable cultural innovations. The mathematical principles that govern information transmission limit the possible structures of human languages, yet these constraints enable, rather than prevent, the endless creativity of human expression. The study of language acquisition reveals how predictable learning mechanisms enable children to master unpredictably complex linguistic systems. Children exposed to any human language naturally discover its grammatical patterns through statistical learning processes that operate below the level of conscious awareness. These learning mechanisms are universal, reflecting the predictable operation of neural development in social environments. Yet each child learns a particular language with its own unique characteristics, and each child contributes to the ongoing creative evolution of that language through their individual usage patterns. The predictable mechanisms of language learning enable the unpredictable creativity of linguistic innovation. This relationship between predictable mechanisms and creative outcomes appears throughout human development. Children develop emotional regulation capabilities through predictable attachment processes. Yet each child develops their own particular personality and emotional style. Cognitive development follows predictable stages of increasing sophistication, yet each child develops their own interests, talents, and ways of understanding the world. The brain mechanisms that underlie these developmental processes exhibit the same combination of predictable structure and creative flexibility. Neural networks develop according to genetic instructions that are largely predictable across different individuals. The basic architecture of sensory processing, motor control, and memory formation follows similar patterns in all healthy human brains. Yet the specific connections that develop within these neural networks reflect the unique experiences and choices of each individual. Every conversation you've had, every book you've read, Every problem you've solved has left subtle traces in the pattern of synaptic connections that constitute your particular brain. These individual patterns create the unique perspective through which you perceive and understand the world. The predictable plasticity of neural development enables this creative individuation. Your brain follows the same basic principles of learning and adaptation that operate in all human brains, yet these principles generate a pattern of neural organization that is uniquely yours. The mathematical laws that govern synaptic strengthening and neural network formation are universal, yet they produce individual minds that are irreducibly particular. This neural creativity operates continuously throughout your lifetime. Every moment of experience triggers cascades of neural activity that subtly modify the strength of synaptic connections. These modifications accumulate over time to create gradually changing patterns of neural organization that reflect your ongoing interaction with the world. The predictable mechanisms of synaptic plasticity ensure that these changes enhance rather than disrupt overall brain function. Neural networks naturally develop toward configurations that improve their ability to process relevant information and generate appropriate responses. This optimization occurs through local learning rules that operate independently in different parts of the brain, yet coordinate to produce coherent improvements in overall cognitive performance. Yet the specific direction of these neural changes depends on the particular experiences and choices that shape individual development. Two people exposed to similar environments will develop similar neural capabilities, but the detailed patterns of their neural organization will reflect their individual histories of perception, action, and reflection. This individual neural development occurs within the broader context of social and cultural evolution that also exhibits predictable patterns and creative innovations. Human societies naturally develop systems of cooperation, communication, and resource management that exhibit similar functional characteristics across different cultural contexts. These universal features reflect predictable constraints imposed by human psychology and environmental challenges. Yet each society develops its own particular solutions to these universal challenges. The specific forms of social organization, cultural expression, and technological development that emerge in different societies cannot be predicted from general principles alone. Cultural evolution involves genuine creativity and historical contingency that generate unprecedented innovations. The development of scientific and mathematical knowledge exemplifies this cultural creativity operating within predictable constraints. All human societies develop some form of systematic knowledge about natural phenomena. Yet the specific theoretical frameworks and investigative methods that emerge vary dramatically across different cultural contexts. The ancient Chinese developed sophisticated astronomical observations and mathematical techniques that were quite different from those developed in ancient Greece or medieval Islamic civilization. Each tradition contributed unique insights and methods that enrich the global development of scientific understanding. Yet, these diverse scientific traditions converged on similar mathematical relationships and natural laws when they investigated the same phenomena. The predictable structure of reality ensures that careful investigation will eventually reveal the same underlying patterns regardless of the cultural context in which the investigation occurs. This convergence of diverse investigative traditions on common mathematical truths demonstrates the objective reality of the patterns that scientific investigation discovers. The fact that different cultures independently develop similar mathematical concepts and physical theories provides strong evidence that these discoveries reflect genuine features of reality rather than arbitrary cultural constructions. The mathematical constant pi appears in calculations performed by mathematicians working in completely different cultural traditions. The inverse square law for gravitational attraction emerges from astronomical observations made by investigators using different theoretical frameworks. The statistical laws governing large numbers are discovered by scholars working with different mathematical notations and conceptual approaches. This mathematical convergence across cultural differences suggests that the predictable patterns we discover through scientific investigation reflect fundamental features of reality that transcend particular human perspectives. The universe appears to be structured in such a way that systematic investigation naturally reveals the same mathematical relationships, regardless of who performs the investigation or what cultural background they bring to their work. This objective reality of mathematical relationships provides a stable foundation for cumulative scientific progress that transcends cultural boundaries. Scientific knowledge developed in one cultural context can be successfully applied in completely different contexts because the underlying natural laws operate consistently regardless of human beliefs or expectations. The global success of scientific technologies demonstrates this cultural transferability of scientific knowledge. Medical treatments developed through research in one country prove effective when applied in other countries with different cultural backgrounds. Agricultural techniques based on biological research can be successfully adapted to different climatic and social conditions. Communication technologies enable coordination across cultural differences that would otherwise create insurmountable barriers to cooperation. This practical success of scientific knowledge provides compelling evidence that scientific investigation does indeed discover objective features of reality. If scientific theories were merely cultural constructions without objective validity, they would not prove useful when applied in different cultural contexts. The universality of scientific knowledge thus supports the broader thesis that reality is genuinely predictable according to mathematical principles that operate independently of human observation or interpretation. The patterns we discover through scientific investigation exist in the world itself, not merely in our descriptions of the world. This objective reality of natural patterns creates a foundation for understanding that transcends individual perspectives and cultural differences. When you gaze up at the night sky, you're seeing the same stars that have guided navigators throughout human history. The gravitational forces that hold planetary systems together operate according to the same mathematical relationships that governed celestial mechanics billions of years before human consciousness evolved. The light from distant galaxies follows the same optical principles that enable your eyes to focus images on your retina. The nuclear reactions that power stellar fusion obey the same quantum mechanical laws that govern the chemical processes in your brain. The mathematical harmony that connects these phenomena across vast scales of space and time reflects the deep unity that underlies the apparent diversity of natural phenomena. This cosmic perspective on predictability can evoke a profound sense of connection and belonging. You are not separate from the mathematical patterns that govern stellar evolution and galactic dynamics. The same physical laws that shape the cosmos also shape the biological processes that sustain your life and the neural processes that enable your consciousness. The carbon atoms in your body were forged in the nuclear furnaces of ancient stars that exploded billions of years ago, scattering their elemental treasures across the cosmos. The calcium in your bones, the iron in your blood, and the oxygen you breathe all originated in stellar processes that followed the same nuclear physics principles that continue to power the sun. This stellar ancestry connects your individual existence to the grandest scales of cosmic evolution. The predictable processes of stellar nucleosynthesis that created the chemical elements essential for life demonstrate that your existence is not accidental, but emerges naturally from the lawful operation of physical processes across cosmic time. The gravitational collapse that formed the solar system, the chemical differentiation that created the Earth, and the biological evolution that produced conscious beings all followed mathematical principles that can be understood and appreciated through scientific investigation. Your capacity to understand these cosmic connections reflects the remarkable fact that the universe has evolved to the point where it can comprehend its own operations through the consciousness of beings like yourself. This self-aware aspect of cosmic evolution suggests that consciousness and understanding are not foreign intrusions into a mechanical universe, but natural expressions of the universe's own creative potential. The same mathematical principles that govern the formation of galaxies and the evolution of stars also enable the emergence of minds capable of discovering and appreciating these mathematical relationships. The recursive nature of this cosmic self-awareness creates a kind of mathematical poetry. The universe understands itself through minds that are themselves products of cosmic evolution. The equations that describe stellar dynamics are discovered by brains that are made of stellar materials. The mathematical beauty that scientists find in natural laws reflects the deep harmony between mind and cosmos. This harmony between mathematical understanding and natural phenomena suggests that beauty itself may be a fundamental aspect of reality, rather than merely a human projection onto neutral facts. The mathematical elegance that characterizes successful scientific theories often guides scientists toward productive research directions, even before empirical confirmation is available. Einstein's general theory of relativity was initially accepted by many physicists largely because of its mathematical beauty and conceptual elegance, even though experimental confirmation took years to achieve. The mathematical harmony of the theory suggested that it captured something essential about the structure of reality. Similarly, the standard model of particle physics achieves remarkable predictive success through mathematical frameworks that exhibit deep symmetries and elegant relationships. The mathematical beauty of these theories provides confidence that they reflect genuine features of physical reality rather than arbitrary human constructions. This connection between mathematical beauty and physical truth suggests that aesthetic sensitivity may be an important guide to understanding natural phenomena. The sense of elegance and harmony that characterizes successful scientific theories may reflect our intuitive recognition of the mathematical principles that govern natural processes. The development of musical harmony provides an interesting parallel to this mathematical aesthetics of scientific theories. Musical intervals that sound harmonious correspond to simple mathematical ratios between sound frequencies. The aesthetic appeal of harmonic relationships reflects the mathematical structure of acoustic phenomena. This connection between musical beauty and mathematical relationships was recognized by ancient philosophers who saw music as a path to understanding cosmic harmony. The same mathematical principles that govern musical consonants were thought to govern the relationships between celestial bodies and the fundamental structure of reality. While we no longer accept the literal truth of ancient theories about celestial music, the underlying intuition about the connection between mathematical harmony and natural beauty continues to inspire both scientific investigation and artistic expression. Composers use mathematical relationships to create aesthetic experiences. Scientists use aesthetic criteria to evaluate theoretical proposals. This integration of mathematical understanding with aesthetic appreciation creates a rich form of engagement with natural phenomena that satisfies both intellectual curiosity and emotional sensibility. Understanding the mathematical principles that govern natural processes enhances rather than diminishes the sense of wonder and beauty that natural phenomena can evoke. The spiral structure of galaxies becomes more rather than less beautiful when understood through the mathematical principles of gravitational dynamics and stellar formation. The intricate patterns of snowflakes become more rather than less fascinating when understood through the mathematical principles of crystallization and symmetry breaking. This enhancement of natural beauty through mathematical understanding suggests that scientific knowledge and aesthetic appreciation are complementary rather than competing ways of engaging with reality. The predictable mathematical structure of natural phenomena provides the foundation for both reliable practical applications and profound aesthetic experiences. The contemplation of mathematical harmony in natural phenomena can induce states of consciousness that feel both intellectually satisfying and emotionally fulfilling. The recognition of elegant mathematical relationships operating throughout the cosmos can evoke feelings of awe, gratitude, and peaceful acceptance that resemble the emotional qualities associated with spiritual experiences. Yet these experiences arise naturally from scientific understanding, rather than requiring supernatural beliefs or mystical interpretations. The mathematical elegance of natural laws is genuinely present in the structure of reality and can be appreciated through careful observation and rigorous analysis. This scientifically grounded sense of cosmic connection provides a stable foundation for meaning and purpose that doesn't depend on faith or wishful thinking. The mathematical principles that govern natural phenomena are objectively discoverable and universally applicable regardless of individual beliefs or cultural backgrounds. The predictable operation of these mathematical principles creates a cosmos that is both rationally comprehensible and aesthetically satisfying. The same logical consistency that enables scientific prediction also creates the mathematical beauty that inspires scientific investigation and artistic expression. As you rest quietly in the gentle awareness of these cosmic connections, let yourself feel the deep comfort that comes from recognizing your place in this vast, mathematically harmonious reality. You are not a stranger in an alien universe, but a natural expression of the same creative processes that form the stars and shape the galaxies. The predictable laws that govern your heartbeat and breathing also govern the rotation of planets and the evolution of solar systems. The mathematical relationships that enable your brain to process information also describe the quantum interactions that power stellar fusion and the gravitational dynamics that organize galactic structure. This mathematical unity creates a cosmos that feels both infinitely vast and intimately familiar. The same principles operate at every scale, from the quantum interactions in your neural synapses to the cosmic expansion that carries galaxies away from each other across billions of light years. The predictable nature of these principles means that this cosmic harmony is not fragile or temporary, but represents the stable foundation of reality itself. The mathematical laws that enable your existence have operated consistently for billions of years and will continue to operate long after your individual lifetime has ended. This temporal stability of natural laws creates a profound sense of continuity that connects your individual existence to the deepest patterns of cosmic evolution. You participate in processes that began with the Big Bang and will continue until the heat death of the universe. Yet your participation is meaningful and significant within the vast temporal context. The consciousness that enables you to understand these cosmic connections represents one of the most remarkable achievements of cosmic evolution. Through your awareness, the universe becomes conscious of its own mathematical beauty and creative potential. This cosmic consciousness is not separate from natural processes, but emerges from the complex organization of matter and energy according to the same mathematical principles that govern all natural phenomena. Your thoughts about cosmic evolution are themselves expressions of cosmic evolution, reaching new levels of self-awareness and creative potential. The predictable mathematical structure that makes this cosmic consciousness possible also ensures that similar forms of awareness may emerge elsewhere in the universe, wherever suitable conditions develop. The same physical and chemical processes that enabled the evolution of consciousness on Earth may be operating throughout the cosmos, creating a vast community of minds capable of appreciating the mathematical beauty of natural laws. This possibility of cosmic consciousness distributed throughout the universe adds another dimension to the meaning and significance of individual awareness. Your understanding of mathematical relationships and natural beauty may be part of a much larger pattern of cosmic self-awareness that connects conscious beings across space and time. Whether or not other conscious beings exist elsewhere in the universe, your own consciousness represents a genuine achievement of cosmic evolution that deserves recognition and appreciation. The mathematical understanding you can achieve during your lifetime contributes to the ongoing creative potential of the cosmos itself. This creative contribution occurs through the practical applications of scientific knowledge that improve life on Earth and expand human capabilities, but it also occurs through the aesthetic appreciation and emotional satisfaction that mathematical understanding can provide. Both practical problem solving and contemplative appreciation represent valuable forms of engagement with the mathematical structure of reality. The integration of practical application with contemplative appreciation creates a balanced approach to scientific understanding that honors both the instrumental value of predictive knowledge and the intrinsic value of mathematical beauty. This balance enables scientific investigation to serve human flourishing in its fullest sense, addressing both material needs and spiritual aspirations through rational inquiry into natural phenomena. As scientific understanding continues to develop and reveal new layers of mathematical harmony in natural phenomena, the potential for both practical application and aesthetic appreciation will continue to expand. Each new discovery opens up new possibilities for technological innovation and new sources of wonder and beauty. The ongoing creative development of scientific knowledge thus represents one of the most hopeful aspects of human existence. Through systematic investigation of predictable natural patterns, we continue to discover new ways to address human challenges and new reasons for appreciation and gratitude. This scientific optimism is grounded in the demonstrated reliability of natural laws and the proven effectiveness of mathematical approaches to understanding complex phenomena. The same predictable principles that have enabled past scientific achievements continue to operate and provide a foundation for future discoveries. The mathematical structure of reality ensures that careful investigation will continue to reveal new insights and applications as our investigative capabilities improve and our theoretical understanding deepens. The universe appears to contain layers of mathematical organization that we have only begun to explore. This inexhaustible richness of natural phenomena provides a source of ongoing wonder and discovery that can sustain intellectual curiosity and aesthetic appreciation throughout human history. Each generation of scientists and mathematicians discovers new aspects of the mathematical harmony that underlies natural processes. The cumulative development of this mathematical understanding creates a growing body of reliable knowledge that serves as a foundation for continued progress. Scientific discoveries build upon previous insights to create increasingly comprehensive and unified theoretical frameworks. This progressive development of scientific understanding demonstrates that the predictable mathematical structure of reality is not a limitation on human creativity, but an enabling condition that makes cumulative knowledge possible. The stable operation of natural laws provides the consistency necessary for systematic investigation and reliable application. In the gentle quietude of this recognition, allow yourself to feel profoundly at peace with the mathematical nature of reality. The predictable patterns that govern natural phenomena are not cold mechanical constraints, but warm, nurturing principles that create the conditions for life, consciousness, and understanding. The same mathematical relationships that seem abstract in scientific equations are intimately present in every breath you take, every heartbeat that sustains you, and every neural process that enables your awareness. Mathematics is not separate from life, but is the deep grammar of life itself. This mathematical foundation of existence creates a reality that is both reliable and meaningful, both rationally comprehensible and aesthetically beautiful. You can trust in the consistency of natural laws while celebrating the creative potential they enable. The predictable mathematical structure of the cosmos provides a stable foundation for hope, purpose, and appreciation that transcends individual circumstances and temporal limitations. Whatever challenges you may face in your particular situation, you remain connected to the eternal mathematical principles that govern the stars and enable the ongoing creative evolution of consciousness throughout the universe. Rest gently in this cosmic mathematical embrace, knowing that you belong fully to this rationally ordered, aesthetically beautiful, creatively evolving reality. The same equations that describe the dance of galaxies also describe the quiet rhythm of your breathing as you drift peacefully into sleep, cradled by the infinite mathematical love that holds all existence together in perfect, predictable harmony, able harmony. This mathematical understanding flows naturally into one of the most intimate aspects of your existence, the predictive nature of your own brain. As you rest here in the quiet darkness, your neural networks are performing millions of calculations every second, constantly generating predictions about what will happen next in your sensory environment. Your brain didn't evolve to passively receive information. It evolved to actively predict the future based on patterns extracted from the past. This predictive capability emerged through millions of years of natural selection, favoring organisms that could anticipate changes in their environment before those changes occurred. Consider the simple act of reaching for a glass of water. Your brain doesn't wait for sensory feedback to guide each movement. Instead, it generates detailed predictions about where your hand should move, how your muscles should contract, and what sensory signals should result from the movement. These predictions are continuously updated based on incoming sensory information, creating the smooth, coordinated action that feels effortless. This predictive processing occurs at every level of your nervous system. Your spinal cord predicts the sensory consequences of reflexive movements, enabling rapid responses to potential threats. Your visual cortex predicts the motion of objects across your visual field, compensating for the delays in neural processing. Your auditory system predicts the continuation of sounds and melodies, enabling you to follow conversations and appreciate music. These neural predictions operate according to the same mathematical principles we've been exploring throughout our journey. Statistical learning algorithms extract patterns from sensory experience. Bayesian inference combines prior expectations with current observations. Information theory quantifies the efficiency of neural coding and transmission. The remarkable success of these biological prediction systems demonstrates that the natural world contains sufficient statistical structure to make prediction possible. If the environment were truly random, neural prediction systems could not have evolved. The fact that your brain can successfully anticipate future events provides direct evidence for the predictable nature of reality. Your visual system provides a beautiful example of this predictive processing. When you watch a ball being thrown through the air, your brain doesn't simply track its current position. Instead, it extracts the mathematical trajectory from the observed motion and predicts where the ball will be by the time visual signals reach your conscious awareness. This predictive capability enables you to catch moving objects, navigate through changing environments, and coordinate your actions with other people. The mathematical computations involved are extraordinarily sophisticated, solving differential equations in real time using neural networks that operate through electrochemical processes. Yet these computations feel effortless because they occur below the threshold of conscious awareness. You don't experience the mathematical complexity of neural prediction any more than you experience the quantum mechanical interactions in your brain cells. The predictive machinery of consciousness operates smoothly and silently, creating the seamless experience of perceiving a coherent, stable world. This neural predictability extends into the realm of memory and learning. Every experience you have creates subtle changes in the strength of synaptic connections throughout your brain. These changes accumulate over time, to create patterns of neural organization that encode your memories and guide your future behavior. The mathematical principles that govern synaptic plasticity ensure that these neural changes enhance rather than disrupt your brain's predictive capabilities. Connections that successfully predict future events are strengthened. Connections that make poor predictions are weakened. This constant optimization process gradually improves your brain's ability to anticipate and respond to environmental challenges. The predictable nature of this learning process creates the possibility of education, skill development, and personal growth. You can deliberately expose yourself to new experiences and practice new skills with confidence that your brain will adapt in ways that improve your capabilities over time. Reading provides a perfect example of this learned predictability. As your eyes move across these words, your brain predicts upcoming letters based on the partial words you've already seen. It predicts upcoming words based on the grammatical structure of the sentence. It predicts the overall meaning based on the context established by previous sentences. These multiple levels of linguistic prediction enable you to read much faster than would be possible if you had to consciously process each letter individually. The predictable statistical structure of written language allows your brain to fill in details and anticipate meanings, creating the fluid experience of understanding written text. The same predictive mechanisms operate in spoken language, musical perception, and social interaction. Your brain continuously generates predictions about what other people will say, how they will behave, and what emotions they will express. These social predictions enable the complex coordination required for human cooperation and communication. The accuracy of these social predictions reflects the existence of predictable patterns in human behavior. Despite the complexity of human psychology, people tend to behave in ways that can be anticipated based on their past behavior, their social context, and the universal features of human nature. This behavioral predictability doesn't mean that people are mechanical or that individual choices are predetermined. Rather, it reflects the operation of psychological and social principles that create statistical regularities in human behavior while still allowing for individual variation and creative choices. Your brain's social prediction systems evolved to exploit these statistical regularities for survival and reproduction. Being able to predict how others will behave provides enormous advantages in competitive and cooperative situations. Those ancestors who could better anticipate social dynamics were more successful in forming alliances, avoiding conflicts, and raising offspring. The modern human brain retains these ancient social prediction capabilities, even in environments very different from those in which they evolved. You still automatically generate predictions about other people's intentions, emotions, and likely behaviors based on subtle cues in their facial expressions, vocal tones, and body language. These social predictions operate so quickly and automatically that they feel like direct perception rather than inference. When you see someone smile, you don't consciously calculate the probability that they're feeling happy. Your brain instantly generates the prediction that they're experiencing positive emotions, creating the immediate sense of understanding their mental state. This immediate quality of social prediction reflects the deep optimization of neural circuits for processing social information. Millions of years of evolution have fine-tuned these systems to extract meaningful patterns from complex social signals with remarkable speed and accuracy. The mathematical principles underlying these social prediction systems are similar to those that govern other forms of neural computation. Statistical learning algorithms extract patterns from social experience. Pattern recognition systems identify familiar social configurations. Prediction mechanisms generate expectations about future social events. Yet social prediction also involves unique computational challenges that distinguish it from purely physical prediction. Other people have minds of their own, with internal states that cannot be directly observed. Social prediction requires inferring these hidden mental states based on observable behaviors and contextual information. This computational challenge has led to the evolution of sophisticated neural systems for what psychologists call theory of mind, the ability to understand that other people have beliefs, desires, and intentions that may differ from your own. These theory of mind systems enable the complex social coordination that characterizes human societies. The predictable operation of theory of mind systems creates the possibility of empathy, cooperation, and cultural transmission. You can understand how others feel, predict how they will respond to different situations, and coordinate your behavior with theirs to achieve shared goals. This social predictability extends beyond individual interactions to encompass larger cultural and institutional patterns. Human societies naturally develop predictable systems of cooperation, communication, and resource management that exhibit similar functional characteristics across different cultural contexts. Legal systems, economic markets, educational institutions, and political organizations all emerge from the interaction of individual behaviors that follow predictable psychological principles. While the specific forms these institutions take vary across cultures, their underlying functions reflect universal features of human nature and social organization. The predictable aspects of social institutions create the stability necessary for complex civilization to develop and persist over time. You can make long-term plans, form lasting relationships, and invest in future outcomes because social systems exhibit sufficient predictability to make these commitments meaningful. Yet social systems also exhibit creativity and historical change that cannot be fully predicted from general principles alone. Cultural evolution involves genuine innovation and adaptation that generates novel solutions to social challenges. This balance between predictable structure and creative change appears to be essential for healthy social development. Societies need enough predictability to maintain cooperation and coordination, but enough flexibility to adapt to changing circumstances and incorporate new insights. The study of complex social systems reveals mathematical patterns that operate across different scales of social organization. Network effects influence how information spreads through populations. Game theory describes strategic interactions between competing groups. Economic principles govern resource allocation and exchange relationships. These mathematical frameworks provide tools for understanding social phenomena, but they don't eliminate the genuine agency and creativity that emerge from human consciousness and choice. People make decisions within predictable constraints, but they also contribute to the ongoing creative evolution of social systems through their individual and collective actions. This relationship between predictable social patterns and individual agency reflects a broader theme in our exploration of predictability. Understanding the mathematical principles that govern complex systems doesn't diminish human freedom or creativity. Instead, it reveals the stable foundation that makes freedom and creativity possible. Your ability to make meaningful choices depends on the predictable operation of your neural systems, the reliable structure of your physical environment, and the stable patterns of social organization that provide context for your decisions. Predictability enables agency rather than constraining it. This enabling aspect of predictability extends throughout the natural world. The reliable operation of physical laws creates the conditions necessary for the emergence and evolution of complex systems. Biological organisms depend on predictable chemical and physical processes for their survival and reproduction. Ecosystems maintain their stability through predictable relationships between different species and their environments. Food webs exhibit mathematical patterns that can be analyzed using network theory and population dynamics. Energy flows through ecosystems according to thermodynamic principles that govern efficiency and sustainability. Yet ecosystems also exhibit emergent properties and adaptive capabilities that cannot be fully predicted from knowledge of their individual components. The resilience of natural systems reflects their ability to maintain essential functions while adapting to changing environmental conditions. This ecological resilience emerges from the interaction of predictable individual behaviors that create flexible collective responses to environmental challenges. Trees respond predictably to changes in light and water availability, yet forests can adapt to climate variations through the collective responses of many individual trees. The mathematical principles that govern these ecological interactions operate across multiple temporal and spatial scales simultaneously. Daily cycles of photosynthesis and respiration follow predictable biochemical rhythms. Seasonal migrations follow predictable responses to environmental cues. Evolutionary adaptations follow predictable responses to selective pressures operating over much longer time periods. Understanding these multi-scale ecological patterns provides insights into how complex systems maintain stability while remaining capable of adaptation and evolution. The same principles apply to other complex systems, from neural networks to economic markets to technological development. This multi-scale perspective on predictability helps explain why both order and creativity are fundamental features of natural systems. Order emerges from the predictable operation of natural laws at each scale. Creativity emerges from the interaction of predictable processes operating at different scales. The development of your own consciousness exemplifies this multi-scale emergence of order and creativity. The biochemical processes in your neurons follow predictable molecular principles. The electrical activity of neural networks follows predictable computational principles. The integration of information across different brain regions follows predictable architectural principles. Yet the subjective experience that emerges from these predictable processes exhibits qualities of awareness, understanding, and creativity that seem to transcend purely mechanical descriptions. Your thoughts, emotions, and insights emerge from neural computation, yet they also contribute to the ongoing creative evolution of human culture and knowledge. This emergent creativity doesn't violate natural laws, but represents their expression at higher levels of organization. The same mathematical principles that govern molecular interactions also enable the emergence of consciousness, creativity, and cultural evolution. The recognition of this continuity between physical processes and mental phenomena provides a unified perspective on the relationship between predictability and creativity throughout nature. Predictable laws enable emergent phenomena that exhibit genuine novelty and creative potential. This unified perspective suggests that the apparent tension between scientific determinism and human agency may be based on a false dichotomy. Understanding the predictable aspects of natural phenomena doesn't eliminate creativity and meaning, but reveals the stable foundation that makes them possible. Your consciousness emerges from predictable neural processes, yet it also contributes to the ongoing creative evolution of reality through your perceptions, insights, and actions. You are simultaneously a product of natural laws and an agent of natural creativity. This dual nature of consciousness, as both determined and determining, reflects the recursive structure of complex systems. Your brain predicts your environment, but your predictions also influence your behavior, which changes your environment, which affects your future predictions. This recursive relationship between prediction and action creates feedback loops that can amplify small changes into significant transformations over time. Individual choices that seem insignificant can cascade through complex systems to produce large-scale changes that reshape entire cultural and technological landscapes. The development of scientific knowledge illustrates this amplification of individual contributions through collective processes. Each scientific discovery builds on previous insights, while also opening up new directions for future investigation. Individual scientists make predictable contributions based on their training and available methods, yet the collective enterprise of science exhibits genuine creativity and progress. This scientific creativity operates within predictable institutional and methodological frameworks while generating genuinely novel insights about natural phenomena. The same principles apply to technological development, artistic expression, and social innovation. Understanding these creative aspects of predictable systems can inspire a sense of meaningful participation in larger processes of development and discovery. Your individual contributions may seem small, yet they participate in collective dynamics that create significant changes over time. This participation occurs through both your practical activities and your contemplative engagement with natural phenomena. Learning about the mathematical structure of reality contributes to the ongoing human project of understanding and appreciating the cosmos. Applying this understanding to practical problems contributes to technological and social development. Both forms of participation reflect the creative potential that emerges from conscious engagement with predictable natural patterns. Understanding natural laws doesn't limit human potential, but expands it by revealing new possibilities for knowledge and application. The history of human civilization demonstrates this expansive effect of scientific understanding. Each advance in mathematical and scientific knowledge has opened up new technological capabilities and cultural possibilities that were previously unimaginable. The development of mathematics enabled architectural achievements like Gothic cathedrals and engineering projects like aqueducts and bridges. The understanding of electromagnetic phenomena enabled the development of electric power and communication technologies. The discovery of quantum mechanics enabled the development of computers and medical imaging devices. Each of these technological developments emerged from understanding predictable natural phenomena. Yet the applications often involved creative insights that could not have been anticipated from the original scientific discoveries. Predictable knowledge provides tools, but creativity determines how those tools are used. This relationship between predictable knowledge and creative application continues to drive human development in directions that remain genuinely open and unpredictable. While we can understand the mathematical principles that will constrain future technological development, we cannot predict exactly what new capabilities will emerge or how they will be applied. This open-ended quality of the future provides space for hope, purpose, and meaningful action, even within a universe that operates according to predictable mathematical laws. Understanding natural patterns enhances rather than diminishes the significance of human choices and creative contributions. The contemplation of this creative potential within predictable natural systems can evoke feelings of wonder and gratitude that enhance the aesthetic dimensions of scientific understanding. The mathematical beauty of natural laws becomes even more compelling when understood as the foundation for ongoing creativity and development. This aesthetic appreciation of predictable natural patterns can provide a source of comfort and inspiration that enriches daily experience. Recognizing the mathematical harmony that underlies natural phenomena can transform ordinary observations into opportunities for contemplative appreciation. The regular rhythm of your heartbeat reflects the same mathematical principles that govern the oscillations of atomic clocks and the pulsations of distant stars. The spiral pattern of water flowing down a drain follows the same geometric relationships that appear in the arms of galaxies and the structure of seashells. These connections between everyday phenomena and cosmic patterns create a sense of participation in something vast and beautiful that transcends individual circumstances and temporal limitations. You are not separate from the mathematical harmony of the cosmos, but intimately connected to it through every aspect of your existence. This cosmic connection operates through the predictable physical and chemical processes that sustain your life, but it also operates through the conscious awareness that enables you to recognize and appreciate these connections. Your understanding of natural patterns represents the universe becoming aware of its own mathematical structure. This recursive self-awareness creates a profound sense of meaning that emerges naturally from scientific understanding without requiring supernatural beliefs or mystical interpretations. The mathematical elegance of natural laws is genuinely present in reality and can be directly appreciated through careful observation and rational analysis. The cultivation of this appreciative awareness can become a form of contemplative practice that integrates intellectual understanding with emotional fulfillment. Recognizing the predictable mathematical patterns that govern natural phenomena can evoke the same kinds of peaceful satisfaction that are traditionally associated with meditation and spiritual reflection. Yet this scientifically grounded contemplation remains firmly rooted in empirical observation and rational analysis. The sense of cosmic connection emerges from understanding real relationships rather than from wishful thinking or imaginative projection. This empirical foundation provides a stable basis for contemplative practice that doesn't depend on faith or belief, but can be verified through direct investigation. Anyone can observe the mathematical patterns in natural phenomena and experience the sense of wonder and appreciation that these observations can evoke. The universality of mathematical relationships ensures that this contemplative appreciation is available to people from any cultural background or personal circumstance. The same geometric principles that create the beauty of flowers also create the elegance of mathematical proofs. The same wave equations that describe the motion of ocean waves also describe the propagation of light and sound. This mathematical universality creates a form of contemplative practice that transcends cultural differences while remaining grounded in objective features of reality. The appreciation of natural patterns can provide a common foundation for human understanding that bridges differences in language, religion, and social background. The development of this appreciative understanding can become a lifelong source of learning and growth that continues to reveal new layers of meaning and beauty. Each advance in scientific knowledge opens up new opportunities for contemplative appreciation of natural phenomena. The recent discoveries in astronomy, for example, have revealed mathematical patterns in the cosmic microwave background that provide direct evidence for the inflationary expansion of the early universe. These patterns can be appreciated both for their scientific significance and for their aesthetic beauty. Similarly, advances in molecular biology have revealed the mathematical elegance of genetic codes and protein structures that govern the fundamental processes of life. These discoveries can be appreciated both for their practical applications in medicine and biotechnology and for their intrinsic beauty as examples of natural design. This integration of practical and aesthetic appreciation reflects the unified nature of scientific understanding. The same mathematical principles that enable technological applications also create the patterns that we find beautiful and meaningful. This unity suggests that the distinction between useful knowledge and beautiful knowledge may be artificial. Understanding natural patterns serves both practical purposes and contemplative purposes, contributing to human flourishing in its fullest sense. The recognition of this unity can inspire a more integrated approach to education and personal development that honors both the instrumental value of scientific knowledge and its intrinsic value as a source of meaning and appreciation. This integrated approach can help address the false dichotomy between scientific and humanistic approaches to understanding reality. Science and contemplative reflection are complementary rather than competing ways of engaging with natural phenomena. The mathematical structure of reality provides the foundation for both reliable practical applications and profound aesthetic experiences. Understanding this structure enhances rather than diminishes the sense of wonder and meaning that natural phenomena can evoke. As you rest quietly in the peaceful awareness of these profound connections, allow yourself to feel the deep comfort that comes from recognizing your intimate participation in the mathematical harmony of existence. The predictable patterns that govern the cosmos are not distant abstractions, but intimate realities that flow through every aspect of your being. The same equations that describe the formation of galaxies also describe the biochemical processes that enable your consciousness. The same geometric principles that create the beauty of crystals also create the elegance of logical reasoning. The same wave functions that govern quantum interactions also enable the neural computations that generate your thoughts and dreams. And this mathematical intimacy creates a reality that feels both infinitely vast and deeply personal. You are simultaneously a tiny speck in an enormous cosmos and a unique center of awareness through which the universe comes to know itself. This paradoxical relationship between cosmic vastness and personal significance reflects the multi-scale nature of mathematical relationships. The same principles operate at every level of reality, creating connections that span from the quantum realm to the cosmic scale. Your individual existence participates in these universal patterns, while also contributing to their ongoing creative evolution. Through your awareness, understanding, and actions, you help to actualize the creative potential that is inherent in the mathematical structure of reality. This creative participation occurs through both grand gestures and quiet moments of appreciation. Learning about natural phenomena, solving practical problems, creating works of art, and simply contemplating the beauty of mathematical relationships all contribute to the ongoing creative evolution of consciousness and culture. The cumulative effect of these individual contributions creates the rich tapestry of human civilization that continues to develop and flourish despite the challenges and uncertainties of historical existence. Each generation builds upon the insights and achievements of previous generations while also contributing new discoveries and innovations. This cumulative development of human understanding and capability demonstrates the creative potential that emerges from conscious engagement with predictable natural patterns. The mathematical structure of reality provides the stable foundation that makes cumulative progress possible. The recognition of this creative potential can inspire a sense of meaningful participation in processes that extend far beyond individual lifetimes. Your contributions to understanding and appreciation become part of the ongoing human project of realizing the creative possibilities inherent in conscious existence. This sense of meaningful participation can provide a source of purpose and fulfillment that transcends immediate concerns and temporary difficulties. Whatever challenges you may face in your particular circumstances, you remain connected to the eternal mathematical principles that govern the creative evolution of consciousness throughout the cosmos. The contemplation of these eternal principles can provide a refuge of peace and stability in the midst of life's inevitable changes and uncertainties. While many aspects of existence remain unpredictable and challenging, the mathematical foundation of reality provides a reliable source of order and meaning. This mathematical foundation operates with perfect consistency regardless of human beliefs, emotions, or desires. The same natural laws that governed the formation of the solar system continue to govern the motion of planets today. The same quantum mechanical principles that enabled the evolution of consciousness continue to operate in your neural networks. This temporal consistency of natural laws creates a profound sense of security and belonging. You exist within a cosmos that operates according to principles that are both comprehensible and reliable. The mathematical relationships that enable your existence will continue to operate long after your individual lifetime has ended. This cosmic continuity provides a stable context for individual existence that transcends the temporary nature of particular circumstances. Your consciousness participates in processes that began with the Big Bang and will continue until the heat death of the universe. Yet your participation is meaningful and significant within this vast temporal context. The finite duration of individual consciousness doesn't diminish its cosmic significance, but rather highlights the preciousness of each moment of awareness. The mathematical principles that enable consciousness operate for billions of years, but they achieve their fullest expression through the brief periods when conscious beings like yourself can appreciate their beauty and meaning. This recognition of cosmic preciousness can transform ordinary experiences into opportunities for profound appreciation. Each breath you take, each thought you think, each moment of understanding represents the universe achieving a form of self-awareness that may be rare and valuable throughout the cosmos. Whether or not other conscious beings exist elsewhere in the universe, your own consciousness represents a genuine achievement of cosmic evolution that deserves recognition and celebration. The mathematical understanding you can achieve during your lifetime contributes to the ongoing creative potential of reality itself. This contribution occurs not only through practical accomplishments, but also through the simple act of conscious appreciation. When you recognize the mathematical beauty of natural phenomena, you actualize possibilities for meaning and value that are inherent in the structure of reality, but require consciousness to be fully realized. This contemplative actualization of cosmic potential creates a form of value that transcends purely practical concerns. The appreciation of mathematical beauty and natural harmony represents an end in itself rather than merely a means to other goals. Yet this intrinsic value doesn't compete with practical applications but complements them. The same understanding that enables technological development also enables contemplative appreciation. Both forms of engagement contribute to the full realization of human potential and cosmic possibility. The integration of practical and contemplative engagement with natural phenomena creates a balanced approach to existence that honors both the instrumental value of scientific knowledge and its intrinsic value as a source of meaning and beauty. This balance can provide a stable foundation for a life of purpose and fulfillment that remains grounded in reality while also reaching toward transcendent values of truth, beauty, and understanding. As you settle deeper into this peaceful recognition of cosmic harmony, let the mathematical elegance of existence wash over you like a gentle tide of understanding. The predictable patterns that govern reality create a cosmos that is simultaneously rational and beautiful, comprehensible and mysterious, stable and creative. The quantum fields that pervade all of space operate according to equations of breathtaking mathematical beauty. The gravitational waves that ripple through space-time follow geometric principles of perfect elegance. The neural networks in your brain process information according to algorithms of remarkable sophistication and efficiency. These mathematical relationships create a reality that feels both intellectually satisfying and emotionally nourishing. Understanding natural patterns provides both practical tools for addressing challenges and contemplative resources for finding meaning and purpose. The predictable nature of these patterns means that this cosmic harmony is not fragile or accidental, but represents the stable foundation of existence itself. The mathematical laws that enable your consciousness operate with absolute reliability, creating a universe that you can trust and rely upon even in the midst of uncertainty and change. This trustworthy mathematical foundation provides a source of deep comfort and security that transcends particular circumstances and temporal limitations. Whatever difficulties you may encounter in your individual journey, you remain held and supported by the eternal principles that govern the creative evolution of consciousness throughout the cosmos. And so we come to rest at the end of our gentle journey through the mathematical heart of existence. Tonight, you have discovered that reality is predictable, not because it imprisons us in rigid fate, but because it provides the stable, nurturing foundation upon which all life, consciousness, and beauty can flourish. The same elegant equations that govern the dance of galaxies also cradle your sleeping breath, the quantum fields that enable your thoughts, and the gravitational embrace that holds our planet in its perfect orbit around the sun. This predictability is not a cage, but a gift, the reliable mathematical poetry that makes memory possible, learning achievable, and tomorrow's sunrise certain. As you drift now into peaceful sleep, rest in the profound comfort that you belong completely to this vast, comprehensible, trustworthy universe, where every heartbeat follows ancient rhythms. Every dream emerges from predictable neural symphonies, and every moment of consciousness participates in the eternal mathematical song that connects all things across space and time in perfect, gentle, everlasting harmony.